Greetings and welcome to a new video. In this video we will discuss the power superposition principle in an electric circuit. We will discuss how we can use this principle and where we cannot use it. That is the purpose of this example. Of course, we will see everything step by step in our calculations and verify this in SPICE simulations. Okay, the question is the following. Given the electric circuit with the values of resistor 4 ohms and the inductor of 50 millihenry, that's actually shown here. And there's also two sources given. One is 10 cosine omega 1 t, so the omega 1 will be given shortly in volts here, the expression for V1, and V2 is 8 cosine omega 2 t. So we like to calculate, that's the question here, the average power absorbed by the resistor R for the following cases. We have two cases. Case 1 is when you have the omega 1 is 100 radians per second and omega 2 is 200 radians per second, so two different frequencies. And the case 2 is where they have the same frequency, so the two sources have the frequency of 100 radians per second. So the solution first, we do the case 1. We look at the superposition principle. That means we activate one source at a time. So the V1 active means V2 will be disabled. That is then actually a short. And when you have then V2 only active, that means then the V1 is disabled. We can go to the frequency domain by changing this the V1 to V1 as a capital letter here, and also here for V2 as a capital letter V2. So now everything is in the frequency domain, so we can use phasors that will then calculate it also easily. This current I1 is because of this V1 only, and this current I2 is because of this V2 only. So V1 is then given in the polar representation as 10 and then with the phase of 0 degrees in volts, of course, here. And here in the V2 is 8 with the phase of 0 degrees again and with the volts. So that's actually from these expressions. But we need to know and remember that these two have different frequencies. So if I now work out the reactance of this inductor here for the case where the omega is 100, so we just use this omega times L formula for the reactance of the inductor. That will give us 100 times 0.05. 5 ohms. So the I1 will be here using actually Ohm's law, that this voltage divided by the impedance seen by this voltage source, that is actually the current, because the current is series in this branch. So we can say V1 is 10 with the phase of 0 degrees over this 4 plus J5 we just determined. Now we need to convert this denominator in the polar representation, so we need to make a magnitude and a phase. That can be done by taking the magnitude of this one and also calculate the phase. We have done this in great detail in previous videos about phasors and complex numbers. So I will skip these steps, and then we have here 6.4 and a phase of 51 degrees. Okay, now we do the following. 10 over 6.4, that is our magnitude here, and the phase of the numerator minus the phase of the denominator, and that's actually shown here. So 10 over 6.4 will be then approximately 1.56. And this is 0 degrees minus 51 degrees is minus 51 degrees. And now the result is here, and this is now the I1. Similar case for the situation where the V2 is only active. The reactance now will change because we have now 200 radians per second, so that will be then 10 ohms. And now our I2 will be this. Now remember that I2 goes from left to right, but our voltage source is here, positive and negative in the frequency domain, so we need to also put a minus sign here. Again, the same situation. The impedance seen by the source is still R plus J XL. And now we put here the correct values. We have now here minus 8. We can now get rid of this minus to put it in the phase. So you make it actually 180 degrees. And you go now from this rectangular or the Cartesian representation to the polar representation again in the similar case as we have done it here. We do here 8 over 10.77. That will here will then 0.743 approximately, and then 180 degrees minus the 68 degrees will give you now 112 degrees. This is now the current here for I2. Okay, now note here, very important, I1 and I2 correspond to different frequencies, therefore they cannot be added like what we do if you have a steady state analysis with one specific frequency. So how to do that? Now, because two sources have different frequencies, the total average power can be calculated in this case using the power superposition. So that means actually the following. The power total we want to calculate is the power 1 plus the power 2, and power 1 is because that due to that V1 only, and power 2 is due to that V2 only. So we know that the average power is then calculated using this formula. So we take the amplitude of the I1 we have here, square that, times R. That's actually the normal formula you know, but you need to also divide by 2 in order to go to the RMS values. And now we have this one. In similar case for the P2, now use I2 squared, so that's actually the amplitude of this one squared times R over 2. So the value will be then 1.56 squared over 2 times 4. That will give us here 4.867 watts. And for this case, we have this as the amplitude for I2 squared over 2 times 4. That will give us 1.104 watts. Now, we can use now the power superposition, add these two up here, and we get here in total 5.971 watts. Okay, now let's now go to the situation for case 2, and now we have exact same procedure. Again, using superposition, activate one source at a time. So this will be shorted, V2. Now the V1 will be shorted. Again, V1 and V2 as the frequency domain representations, and then I1 and I2. And again here the representations in the polar form. Now they have the same frequency. So this is a different situation. And now we can say that XL here is omega 1. It will be then of course 5 ohms here in the same manner, and we can calculate again this. This is done of course before. Now this is not changing, exact same result. Now the omega 2 here will be again 100 because that is the same thing. So we just repeat here the calculation. The only change is that we need the minus sign here and our V2 is different. So that is what we need, and now we do here 8 and then cos in the phase of 180 degrees. So because this minus means actually you flip the sign of your signal. And again, we calculate this, and this is actually exact same as this impedance. And when you do the math here, you get here 1.25 amps and with an angle of 129 degrees. Now, because the two sources have the same frequency, we can add these phasor currents I1 and I2. So that can be done like so. I is equal to I1 plus I2, again all in the frequency domain. So we need to add these two. And in order to add these two easily, we need to convert this polar representation here, polar representation there in the Cartesian form or rectangular form. That can be done like so. So you take out the amplitude and then times the cosine of this angle plus the J sine of this angle. So that is actually converting to the rectangular form formula. And now again this 1.25 out, and then in the parentheses again the cosine of this angle plus the J sine of that angle. That's the template you need to use. Now we have it, you just calculate here out the real value, here imaginary value, that's this part. For these two actually coming from this expression, and this expression will result this. Now adding up the real values and the imaginary values, this is the result, final result, subtotal from here in the rectangular form. Again, in order to do the calculations easily, we need to convert that to the polar representation, and that's shown here. Then the total average power will be then the P is then I squared over 2 times R, which is then this amplitude here. So we need to do that. So 0.3097 squared over 2 times 4, because that's the resistor, 4 ohms, and then you get here 0.1918 watts. Okay, now again here we cannot use the superposition principle in the power domain, so the power superposition principle is not allowed. We use here the power superposition principle, that is not power superposition principle, because the two sources have the same frequency. That is the main difference between case 1 and case 2. We can see here the results, case 1 with 2 different frequencies and case 2 with the same frequency, and you see here the I1 is not changing, but I2 will change. That will have an effect, of course, on the power. You see the power is then different from the first and the second case. Okay, and these are the results in the simulations for case 1 and for case 2. Of course, we need to see that also in action in the SPICE simulator. So I will now jump to the SPICE simulator and show you how I generate these values and how you can connect these power meter here in order to get the results there. So let's now jump to the SPICE simulator. So we are now in the SPICE simulator, TINA TI SPICE. I have here now the 2 cases, case 1 left, case 2 on the right side. We have for the case 1, VA, it was given as, let me click on it, you can see that it was a cosine function with an amplitude of 10 volts and the frequency was 100 radians per second, but we need to of course go to the hertz, so you do divide by 2 pi. So 100 over 2 pi, you get this 15.92 approximately hertz. That's for the VA. You also do that for the VB, and that was exact same cosine function, but of course a different amplitude. And now the frequency was there 200 radians per second, so you divide by again 2 pi and you get the 31.82 hertz approximately. So that's what we substitute for the two sources, and now we have the resistor R of 4 ohms and the inductor of 50 millihenries. This is the watt meter that can be inserted from here, so you get here and then you do watt power meter or watt meter, and what you see is this solid line is what the current is measuring. So this element will then measure the current from left to right, and it will now measure now from this thin line, it is the voltage across the element. Now in this case we are interested in the power of our resistor, so which is the average power or the effective power. So we place the measurement of the voltage across this element, so plus here and a minus there, and the current is of course in this case series, so you can actually connect it like so. Exact same is done here on the right side for the case 2, but there we have the same frequency, so 100 radians per second, so the sources are exact same. The frequency here is exact same as in case 1. The only change is here actually, so we make this also 15.92 hertz approximately. So that's the only change. Now what you now can do, you can go to analysis and do here the AC analysis, because we do AC sources, and now you do calculate node voltages. That will give you right away display here the power. You can see that here. So it is almost actually very close to what we have calculated, also what we have discussed. Now we can also do that here on the right side. Again, we go to analysis, AC analysis, and do this. And you see here also the result. So you can also click on the specific elements, for example this one. You can see how much current is flowing there and what kind of a voltage, the phase, etc. You see also this minus 51 degrees we have seen before in our calculations. You can also do that the same here. If you click on this one, you see also here this 112 degrees actually for our current. Alright, it was our example considering the power superposition principle. We have considered two cases and illustrated where we can use the power superposition principle, where not. If you have any questions, comments, please let me know in the comment section. I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video.